Hey everybody, and welcome to our next presentation on vertical motor operation and repair presented by Chuck Young. This presentation is being brought to you by ABB, and this message is provided by them. If you have pump customers looking for a cost-effective solution for wastewater, oil, gas, or chemical processing applications, look no further than ABB's Baldor Reliance IEEE 841XL P-base vertical solid shaft motors. The features of these motors make it an excellent choice for those applications that would benefit from longer service life and reduced maintenance. These motors are now available from stock in locations across the country, and they come with 3 different bearing designs to support all of your customers' thrust load requirements. IP56 standard sealing provides superior protection from ingress and oil containments, and the premium efficient winding and solution system is designed for inverter use. The Baldor Reliance 841XL P-base vertical solid shaft motor is engineered to provide the highest efficiency and reliability under the harshest conditions. It has been designed to suit any of your customers' pumping needs and provide years of uninterrupted service. And now here's Chuck.
Thank you, Matt. Welcome, everybody. So we're going to be talking about vertical bearing systems, vertical bearing motor repair and operation. There's a lot of good information in here that we've gleaned over, well, in my case, 47 years, and in Tom's case, even longer. So a lot of good information that we've compiled over the decades, really. So just another one of the values of ESA membership is all the information that we've got here. So this first slide looks a little bit busy, a little bit technical. What I'm really trying to show here is that when you compare a horizontal motor, where all we're supporting is the weight of the rotor and then possibly a radial load if we have a large sheave or pulley on the end of the shaft, compare that to a vertical motor where we're not only supporting the weight of the rotor, but also a thrust load that may run into the thousands or even tens of thousands of pounds. So if you have a vertical motor with a fairly nominal thrust load, it may have what looks like just a normal ball bearing on the bottom and on the top. You may have a smaller, fairly low thrust load where you might have a thrust bearing on the bottom. But in most cases, we're dealing with larger machines where we have 1, 2, or 3, and in some rare cases, even 4 thrust bearings on top. So we're looking at the thrust capacity here, and that's what determines the bearings that we need on top. You know, what's the thrust load? What's the customer's application? So we're going to talk about that, but just as a real quickie, any kind of radial load typically is limited to no more than about half the thrust capacity of a thrust bearing. So we'll talk about thrust bearings here. There's some interesting things. Well, you know, electric motors are pretty fascinating, honestly. So there's some pretty interesting things. If we look at a fairly typical medium thrust vertical motor, we may have 1 or 2 thrust bearings, both thrust down, and we usually have an oil metering plug or an orifice that kind of regulates how much oil can get into the bearing. It lubricates this bearing, gets slung up here for this one and over the top and mixes into this outer chamber, which is usually a fairly good capacity, in some cases quite a few gallons. So that cools the oil that's just exited the bearing, and the metering plate regulates how much oil comes in. So there's some things that we'll talk about. We're going to talk about the bearing carrier itself. We're going to talk about the shaft fit. We're going to talk about thrust bearing direction or orientation and capacities and that sort of thing here. So typically angular contact thrust bearings used for pumps, usually almost exclusively for large pumping applications. The bearing can have as a contact angle as great as 40 degrees. So we may have anywhere from 10 to 40 degree contact angle. And it's really important that we're cognizant of what bearings it came in with. And we always have to balance that with what could somebody else have messed up on working on it previously? So the key, like with all motors, is asking the customer, how long's it been in service? Have you had problems with it? Why did you send it in to us? And sometimes without those prompts, they won't say, well, you know, it's only been in for 3 months and we bought this surplus from somewhere across the country and it hasn't run right. So if they don't tell us that, then we don't know what kinds of stuff to look at here. So we have to have a significant axial thrust load, enough to keep the bearing loaded so that it doesn't orbit. If we're running unloaded, that top end may actually begin to orbit and you'll see some subharmonic vibration, that sort of stuff. And it's liable to be noisy because the rotor weight is not always enough to keep the thrust bearing mated up and keep those balls rolling instead of skidding or sliding. The bearing retainer, the cage, some of these are a molded plastic, which are actually very much better than what we seem to think. We kind of have an aversion to plastic. We can have pressed steel, what are often labeled as farm duty, and then we can have a bronze retainer. We really want a machined bronze retainer rather than pressed for most of these applications for larger electric motors. And that machined bronze retainer, we have to even delve further into that. It could be guided on the inner race, it could be guided on the outer race, or it could be ball guided. And the ball guided is preferred because it's going to give you better lubrication and therefore better cooling. So if we looked at these, this one, the brass cage or bronze cage, is very close distance to the inner race. This one, it's a very close distance to the outer race. So this is inner ring guided. This is outer ring or outer race guided. And what you want is the ball guided, in which case you can see a pretty significant gap between that bronze cage and the outer race, and a similar gap between the bronze cage and the inner race. And you can see just visually, this is going to allow the oil to flow up through the bearing, circulate, cool the bearing, lubricate the bearing, and not have any obstructions to the lubrication. So that's really important. I almost think this slide is better than the next one, but here from one bearing manufacturer, this is race guided or ring guided, where the cage is very close, almost in contact with one of the races, in this case the inner race, versus here the ball guided, where that cage, that bronze retainer, is more or less centered. It actually is floating on the balls, keeping the balls spaced, of course, which is what the bearing retainer is supposed to do, but it also is here where it's not obstructing our ability of oil to flow through. And the more bearings we have stacked, the more important this becomes, because we may have as many as 3 thrust bearings stacked, and the oil in this case would have a difficult time getting through and getting to that uppermost bearing, whereas in this one, the ball guided bronze cage is going to be able to allow the oil to flow through and cool the bearings and lubricate them the way we want. If you've got the accompanying paper, you'll see that I use 2 different sets of terms because the different motor manufacturers have different terminology that they use. So one we'll call a low thrust application or a low thrust motor, which is just going to have a normal deep groove Conrad ball bearing, a same bearing that you would have in a horizontal machine. What one manufacturer calls a medium thrust and another calls a low to medium thrust would call for one angular contact thrust bearing. So your 7320 or whatever the number is, single thrust bearing. Medium to high thrust may have 2 or even 3 thrust bearings, and we're going to talk about speed ratings in just a few slides and how that factors in how that comes into play in determining how many thrust bearings we're going to use or require for that particular motor. And then what I'm calling through the paper high thrust would usually be a spherical roller thrust bearing. So that's the one where you have a coned outer race spherical rollers that ride on this. And these are often even spring loaded. And we're going to talk a little bit about some of the precautions in how we operate these, how long we can run them safely without a thrust load on them. And there are some real precautions that we need to be aware of. And then we have the very high thrust, which would be the hydrodynamic bearings. Kingsbury being the most easily recognized name, probably. Huge life improvement with the hydrodynamic bearing, but they're really restricted in terms of, this is a great bearing if you're a hydro generator, where you start once in the spring when the water's up and you run all summer and you run into the fall until the water flow diminishes enough that you can't produce, and then you turn it off. So if you're a bearing, that's a pretty good life. This is a terrible bearing for an application that might start multiple times a day. So those are sort of trade-offs. And if we looked at a cost comparison, and that's a factor for the manufacturer and for the customers, that our industry serves, the cost for, let's say, a hydrodynamic bearing that can support 20,000 pounds would be about 10 to 15 times the dollar value, or anyway, 10 to 15 times the cost of a comparable spherical roller thrust bearing that's rated for the same load. So the hydrodynamic bearing is not really something that we see except in applications where it is a very infrequent starting and it just runs more or less continuously. So once again, the hydro generators, vertical hydros, that's a real common place to see this. So let's talk about how much bang we get for our buck. If we have a single thrust bearing, and just for the ease of numbers here, I'm using a single thrust bearing being rated at 10,000 pounds capacity, we only get 60% more thrust capacity over the original bearing for each additional bearing. So 10,000 pound capacity, if we put a second bearing in, we're only bumping it up to 16,000 pounds, but we've doubled the cost of our bearings. Adding a third bearing, now we're at barely over twice the capacity of the first bearing, but we're at 3 times the cost. So you can see it's not something a manufacturer wants to do unless there are some other qualifying reasons why they have to do this. One of these is the speed rating of the thrust bearing. It kind of makes sense. The larger the diameter, the higher the peripheral speed, and the more constrained we are by the size of the bearing for the speed rating. So the manufacturer, the designer, may have no choice if they need to meet a specific thrust load and they need to have, say, a 3,600 RPM motor, then they may have to use a stack of smaller diameter bearings in order to fall within the speed rating of the bearing and have a good L10 life, and yet still have the thrust capacity that they're after. And of course, if we have an application, which we frequently do, where we have 1 or 2 thrust bearings thrust down and then 1 thrust up to handle momentary upthrust for some sorts of applications, then we still have only the thrust capacity of the 2 thrust down, and the third bearing is adding cost, but it's only helping us to handle upthrust. So if you look at different motor manufacturers, there are 2 that produce most of the vertical motors that are in use out there, but there are a whole bunch of other manufacturers who also do build vertical machines and do so successfully. So sometimes you'll see, if you're comparing different manufacturers, you may see that, well, gee, this manufacturer doesn't usually use a bearing thrust up, but they do have a bigger guide bearing on the bottom of the motor. And that's because that manufacturer may have decided that they're going to handle their up thrust by sort of making that bottom guide bearing do double duty. They're saying, hey, this is just sitting here guiding this shaft, keeping everything centered. Let's use a little bigger bearing there and get more bang for our buck. So that allows them to avoid stacking multiple thrust bearings on the top end, because the more thrust bearings we stack, the more issues we have with cooling and lubrication. So more on that in just a few minutes here. So this is a place where we really have to pay attention dismantling and inspecting motors. If there's no suffix on the thrust bearing, if it's just, for example, 7320, then it has a quote unquote standard contact angle of 30 degrees. If it's a suffix B as in Bravo, then it's got a 40-degree contact angle. And if it has a suffix C as in Charlie, then it's only a 15-degree contact angle. So why do we see those different contact angles used, and what do we need to be aware of? Well, for starters, the smaller the contact angle, the more stable it is radially. So we have a higher speed capability, but because it's that steeper angle, we don't have as much thrust load capability. And because of that, at a given load, we're going to have a decreased bearing life. Higher contact angle, greater load capacity. But if you ever watched race cars on a dirt track, you know, if you've got a pretty steep bank here, it's a lot more likely for the balls to track up the sides and give you that orbiting issue. So greater load capacity, which is great, but we have to recognize that we have to keep the thrust load on that. So when we're dismantling and inspecting a motor, you want to make really sure the mechanics are looking at the bearing number on each of the thrust bearings, whether they're 2 or 3 or even 4. Make sure that they're not only paying attention to what the number is, but for instance, if you have one without a suffix and one that's a B, then you have what some people would call a pump pack. So a set of bearings where one has a higher angle of contact to give you the load carrying capacity, and one has a much lesser angle of contact in order to keep everything centered radially and prevent orbiting. That's a more commonly seen on 3600 RPM vertical motors, where we might have a mix of those. And I'm going to toggle back just to touch base on this. So 40-degree angle of contact, higher load capacity, 15-degree angle of contact, better stability for higher speed. So we often see a combination of these. So really important that if your mechanic is cognizant of the fact that they really need to document the number on each bearing, especially if they find they've got two different angles of contact. So a B with no suffix or a B with a C, that they need to document that, and they really want to document the relative position, which one was on top. So that's something that we really have to stress. And as always, keep in mind that vertical motors are expensive, not easily replaced, and consequently this may have been dismantled and repaired many times over a 50 or 60 year motor life. So there's always the possibility that someone has missed the designation of the bearings and used the wrong bearings. So real important to have a good relationship with your customer. You know, how's this motor been running for you? Do you have any vibration spectra that you can shoot past us so we can look and see what's going on? And I think those things are really helpful here. So again, if we're stacking multiple thrust bearings, because we have a higher thrust load capacity, and maybe because we have a high enough peripheral speed that we can't go with one big thrust bearing that would carry the thrust load, we may be stacking these. So the downside is harder to get oil pushed up through each bearing, particularly if we have more than two. And if we have increased heating, heat is losses. So that's an efficiency ding. We may find that because of the higher temperatures, we need to add cooling coils to the chamber. Frequently see this from some manufacturers, but just because it didn't come in with a cooling tube, if you know your customer's got heating issues, then that's something that an aftermarket improvement that we can do. For the managers in the room and company owners, that's a billable extra. We like billable extras, right? So if we have two thrust bearings thrust down, then pretty straightforward. We have our oil metering orifice to regulate the oil coming in, and pretty straightforward. One thing that, and I've had this call as recently as late last week, one thing we really have to educate our customers about is not just the oil level, but because this orifice here is usually quite small, under 1/4 inch, it regulates how much oil flows through. But when the motor's at standstill, liquid seeks its own level. So the oil level inside and in the oil chamber are going to be at the same level. But an impatient customer installs the motor, couples it up, connects the leads, and the last thing they do is, oh yeah, we've got to fill it with oil. So if they pour oil into the fill plug and they bring it up to the correct mark on the sight glass, they may need to let this sit for an hour to make sure that the oil has metered through here and that we actually have the correct amount of oil in here. Helped someone recently with one that was supposed to take 32 quarts, and the customer was over 1.5 gallons low because they got impatient. They filled the oil level to the right point on the sight glass, and they didn't wait for the oil to seep through and truly be at the right level. So they were literally 1.5 gallons low on the oil level, and no surprise, they lost a pair of pretty expensive thrust bearings. So good thing to educate the customer about. We don't want to ship motors with oil for a lot of good reasons, but we do want to educate the customer, hey, once you've set it and bolted it down, start one guy filling the oil level while someone else is connecting the leads and coupling it and so forth. And for goodness sake, give it enough time to, for the oil to truly be at the right level. I know of some of you service centers where you actually put a nameplate with the oil capacity on the outside of the motor. So, kudos to you. That's a good way to help keep a customer from making one of those mistakes.
Hey, Chuck, we got a
So
quick question.
Sure.
The question is, if the original bearing 7320B is replaced with 7320 BEM, will it function the same?
Yes, good question. So the B designation, no designation, the B or the C have to do with the contact angle. E is one of the more popular bearing manufacturers' designation for what they call a high RPM bearing, a higher speed rating. If you can imagine, they have even greater precision in the manufacturing to allow that. And then the M is the machined bronze retainer. So when we look at the different designations, those additional letters, and thank goodness for online capabilities. You can either look at a paper catalog, which I like because I'm old, or you can look at the online catalogs and see exactly what those suffixes stand for. So good question, thank you. So we've already looked at the bearings and how we don't get as much bang for our buck when we add additional thrust bearings, and it really is a speed rating sort of thing. So in terms of adding bearings, you usually are seeing these at motors that operate at a higher RPM. And although I've not covered it in this material, I think that when we start talking with customers who love VFDs, we kind of have to worry about not only the affinity laws driving a pump at an increased speed, but also we have to worry about the speed rating of the bearings as well. So kind of an interesting aside. Might be a good future currents article. So if we look at this vertical motor with two thrust bearings, one thrust up, one thrust down, there are some things here that don't readily come to mind for most of us. One, of course, and I think it's obvious, is if we have a thrust bearing thrust down and we have a thrust bearing thrust up, then we've got to have something not only clamping the outer races in the housing, so there's something to thrust up against, but we also need something to keep the thrust bearings on the bearing carrier. Usually that's a little flat spiral lock snap ring, but sometimes we do see a bearing lock nut used here. Going to turn the oil more, so it's not as popular as the little spiral lock snap ring, but you do see those. And the other thing, and I think you can see in the slide here, there's a shoulder on the shaft. So this bearing carrier, this bearing hub, has to shoulder out on the shaft, and then our bearing lock nut clamps the bearing carrier. So we have the outer races clamped in the housing, so there's something to thrust up against, so it doesn't just lift the bearings in the housing and, you know, lift shaft and all. We also have to have the bearing inner races clamped on the bearing carrier, because that hollow shaft, it's pretty easy to displace an inner race on that bearing carrier. But we also need that upper portion, we need that shouldered on the shaft. So we're actually clamping this hub, this bearing carrier, on the shaft. We're clamping the outer races and we're securing the inner races. We really need all three of those things together if we have much potential for an upthrust. And the takeaway here, when we start talking about setting in play or in thrust, the part of the takeaway is, hey guys, we don't use the usual methods of backing off this nut and dropping the shaft 8 or 10 thousandths. We actually want, in this case, the design is for this to be clamped. So when we're dismantling, that's one of the things we want to look at. Is there a fit here that's approximately the height of the fit portion of the bearing carrier? And if so, it looks like this should be clamped on the shaft. Make a note of that, document that for the sake of the mechanic who's assembling it, so that we don't make a simple mistake here. So thrust bearings back to back, usually what we like to see, and not all manufacturers or shops do this, what we want to see is most of the time we're operating with a down thrust. So what we want to see is the up thrust bearing being on the bottom, because it's not carrying any load, so it's really not generating much heat. So we're getting a little bit cooler oil up here to cool the upper bearing, which is the one that's oriented thrust down. So we can do it the other way, but this is the preferred way to mount this when you have a pair of bearings, one thrust up, one thrust down. The extra high thrust may be a spherical roller thrust bearing like this, which has a set of very stiff springs beneath the outer race. And those serve two purposes. One is they keep the bearings pieces mated together. If there's an event, a brief upthrust, they're going to move together. And the other thing is that when the down thrust is restored, those springs act as a cushion so that we don't have a sudden shock load. If you've ever dismantled a vertical motor with a spherical thrust bearing and you see lots of big dinged, chipped areas in the outer race, that's very likely because it's a motor that was built without these springs to cushion that thrust load. So it's very often an impact damage. So I think that's something to certainly pay attention to. Could also be the hydrodynamic bearing. So what's called a sliding plate bearing. We have these thrust bearing shoes supported on these leveling plates. And these kind of act like the old childhood sawhorses, seahorses, where they rock back and forth. And what's pretty simple, deceptively simple, really, the bearing carrier, the thrust runner here, is supported on these individual thrust shoes, which are here, here, and here. And because the bottom of each of these has a protrusion that rests on this portion of the leveling plate, this automatically shares the load that's placed on it between this one and this one. So you can see what happens. You sort of have a daisy chain. You have a bunch of identical thrust runners resting on the upper piece of the leveling plate, and in each of those in turn dividing the weight it's carrying between the two adjacent ones. So this by default means that each of these pivoted shoes of the thrust bearing, each of these is actually carrying the same thrust load. So very, very slick design, very intelligent design. But again, if you look at this and you say, well, we might have thousands and thousands or tens of thousands of pounds of weight supported on this thrust runner, it's going to squeeze all the oil out from the underside of the thrust runner and the top of the thrust bearing portion. So each of these pads, it's going to be a dry start. So in the service center, what we typically will do is either put a bottle jack under the shaft to lift it up 10 or 15 thousandths, or use an overhead crane with an eye bolt to do the same. So we're just going to pick the shaft up just enough to get the thrust runner off of the bearing pivot pads, give it a spin so that we start some oil between these two surfaces, and then we go ahead and start it and run it. So we really don't want a dry start. We really want to have oil between those two surfaces to minimize friction. We're a lot more likely with this design. It may have 30 or 40 or 50 gallons of oil here. There's quite a bit of heat being generated here. So we're very likely to have cooling tubes here. So the cooling tubes, we'll talk about cooling tubes specifically in just a few slides, because we do see them with conventional thrust bearings as well, but there's some important things to look at with this. So when we talk about the oil, 30, 40, 50 gallons of oil in a machine this size, oil contains about 10% dissolved air at room temperature. So there's a little bit of air entrained in the oil, so we're always cognizant of that. If we have some foam on the surface of the oil, really not a big deal. If we've got bubbles throughout the oil, now we have a whole lot more than our 10 or 12% of air, and now we have air entrainment, and we could get vibration, we could get oil oxidation, problems like that. If we shut it off and the foam on the top disappears quickly, it's probably a mechanical reason for that oil to be foaming. So check for sharp corners, for burrs, not just in the oil chamber, but in particular on the bearing carrier, anything that's moving in the oil. If we've got sharp corners, chamfer them, break them with a file, turn the machinist loose. If the foam remains for quite a while and it very slowly dissipates, then we probably have contamination. Could be solvent from somebody cleaning the bearing housing and not, truly wiping it out, flushing it out thoroughly. And if it looks milky, emulsified, then it's very likely water. So in that case, we want to check the top cap assembly, make sure we have gaskets in place, that everything's properly sealed. It's very possible that our customer might have done something, like pull off the top cap to inspect the bearing and not sealed it back up. So that's something to look for. And in humid climates, it could always be a condensation sort of an issue, so worth looking at. Oil temperature, same 80, 90, 100 rule as for ball bearings. If we have a cooling tube, fill it with water, plug one end, and connect your airline and pressurize it, pressure test it. Most of us are just hooking up our our city water pressure. And if my city water pressure is 40 PSI and the customer's is 65 PSI, then I'm not really adequately pressure testing it. So we want to fill it with water, plug one in, connect an air line with a regulator, and pressure test it something a bit higher than what the customer's actual water pressure is. If you want standards for vertical motors, IEEE 841 touches on it. API 610 is a lot more in depth, so that's worth looking at. Lower guide bearing, it should never carry any thrust load. So when we look at a vertical motor and the bottom guide bearing has failed, question number one, hey, Mr. Customer, how long has this been in service? If they say, well, we just put it in, it's been in the warehouse, whoever worked on it last didn't properly set the in thrust. So this motor will run all day in the service shop uncoupled, but if we haven't set the thrust properly to allow room for thermal expansion of the shaft to prevent preloading that bottom guide bearing, then this is what it's going to look like. So we always want to make sure to check in thrust. So what we're doing when we set in play or thrust is if we have a spherical thrust bearing that's spring loaded in the top, we may need to rig a bottle jack or a chain or a strong back like this and compress those springs, and then we're lifting the shaft. And when we say 8 to 10 thousandths or 6 to 8 thousandths or 6 to 12, the different numbers that many of us use, what we're really doing is we're basically recognizing that we have to lift the shaft as high as possible so that the bottom guide bearing is in contact with the bearing cap, and that's where that really small number, that 6 to 10 thousandths or 8 to 12, whatever the number you're using is, that's where that number comes into play. We're bringing the shaft all the way up until we're shouldering this bottom guide bearing against the bearing cap above it, and then we're backing it off using a dial indicator to drop it just enough that we're not preloaded against that bearing cap, and now we have as much room as possible beneath the lower guide bearing for thermal expansion of the shaft. So that's really what we're doing here. If one guy says, oh, we always set it at 6 to 10, and someone else says, no, 8 to 12, doesn't really matter. If you're in that ballpark, you're good to go. If we have one thrust bearing thrust up, we probably have this bearing carrier shouldered. Outer races are clamped. Thrust up bearing ought to be the lower bearing, just for cooling is really the only reason to do that. And depending on the manufacturer and the extent of how often and how long they may see that up thrust, the bearing carrier is oftentimes clamped against the shaft shoulder. So other mechanical issues to kind of watch for, and there's several here. One is the anti-rotation device, the backstop non-reverse ratchet. We have different names for these. And another thing is the cooling coils. And then the next thing is the bottom bracket flange run out. So let's talk about this first because I have this table here. If we have a 12-inch flange diameter, the rabbet diameter run out radially, 3 thousandths. The face run out, 4 thousandths. And you can see the larger the flange, the more permissible run out we have. Two different types of non-reverse ratchets. One is the ball type and the other is the pin type. If we have the pins, these have to be hardened and they're just about the same hardness of the rollers on a roller bearing. And likewise, the balls for the ball type are about the hardness of the balls in a ball bearing. So with this type, the main thing we want to worry about with either one is when we get ready to test run it in the shop, run it before we add the non-reverse ratchet. And with this type, once we drop the balls into these angled holes, there's a sort of a collar that slips around the outside of those holes to keep those balls from coming out. I remember a shop in the Northeast where I saw the after effect. Mechanic had assembled a pretty good sized vertical motor, dropped the balls in, and then said, oh, I need to check it for rotation. So instead of using a magnet and pulling the balls out, he carried it over to the test panel, connected the test panel, and he didn't put that retaining collar on. He hit the start button, and wouldn't you know it, he had the direction of rotation right. So if you can vision a Gatling gun just about with projectiles this diameter, they had a neat row of holes in the sheet metal wall around the test panel. So kind of a don't do what this guy did. The other thing that's with this pin type is you don't have that issue, but the pins do have to be a hardened material. If they were lost in a previous repair, or the customer removed stuff, shipped it to you in parts and lost those pins, you can't just use conventional bar stock, because each time this motor starts, those pins hit this ramp and they bounce up, and they are held in position by centrifugal force, very slick. But the thing we have to watch here is, if those are not hardened material, those pins are going to mushroom just a little bit more each time they strike that ramp and are driven up. And eventually what happens is, if those pins are allowed to mushroom like that, you wind up with the pins that one day they start the motor and they've now mushroomed to the perfect size, and you turn the motor off and the pins don't drop back down. So you can see where that would be a problem for a pump application. Things to look at. Let's say that the customer says, well, we've changed the pump, and the original pump had 3 thrust bearings, or required 3 thrust bearings, and now we only need 1 thrust bearing because they have a much lower thrust requirement. So in that case, if it was built from the factory like that, of course, you'd have these nicely machined pieces. You don't have to make replacements. Just use 2 of the old thrust bearing outer races. But remember that whichever thrust bearing is being used needs to be in the uppermost position in the chamber. So if we had 2 thrust bearings, we're going to add a spacer beneath and put the thrust bearing here. If it had 3, we're going to put 2 spacers. So the thrust bearing that's in use is in the uppermost position from where the thrust bearings were before. Oil leaks. Got some pretty good slides here. So of course, as repairers, we all know that we don't ship a motor with oil because of all the capillary action and seeping and spillage that can occur. But our customers, that's why you guys are the experts. Our customers don't know all that. Oftentimes, they'll ship you a vertical motor without draining the oil. If it's a rough road, a very long haul back, or even if they had crane issues in handling the vertical, you could take it apart and find a whole bunch of oil in the bottom end bracket, maybe on the rotor, which tells you, well, maybe it was a shipping issue. Maybe it was a leak somewhere internal to the motor. So depending on how much oil is pooled here and the condition and coloration of the oil, it's going to give you some ideas what to look for. But we're going to look at the stand tubes, and there are several things to look at. First one is that this stand tube, if it's bumped during the assembly process, it could get knocked loose, and the epoxy seal could then become a leak. So we may see a very gradual oil leak, but there are other things that can cause a leak. So the bearing carrier here fits down around the stand tube, doesn't make contact. It may have a 1/4 inch or more clearance, so 8-10 millimeters, and it's always going to have clearance here. So the things that could cause oil to leak over here, one would be handling. If the customer overfilled it or jostled the motor, or heaven forbid laid the motor on its side so they could haul it to where they wanted to install it. Any of those things could result in oil over the stand tube. And now, because of a combination of surface tension of the oil and capillary effect, we may have a very slow leak as the oil continues to just siphon extremely slowly out of the chamber and over the stand tube. So that's a possibility. The other thing to look at is when we machine this bearing carrier, be it at the factory or if we've had to do repairs to it or someone else has affected repairs, if they machine this bore, disengage the lathe compound, crank the compound back by hand without moving the tool away from the surface they were machining, we get this barely visible little witness mark, this little thread, and that's the crudest form of an oil pump. That's an Archimedes screw. So Murphy's Law is that if you're running it one direction and you have a thread on the inside, it's going to become an oil pump lifting oil out to where it hits here, where the bearing carrier is shouldered on the shaft, and it pools there, and then it runs down the inside of the stand tube or runs down the shaft through the stand tube. So easy thing to check, very easy thing to overlook. And if you find this, of course, flapper wheel, polish out the bore, have the machinist polish the bore. There are also some designs, and one manufacturer fairly routinely, when they manufacture these at the factory, they machine this portion, this skirt, they machine it on a very slight outward taper so that centrifugal force always is slinging out, and because it's smaller at the top, bigger at the bottom, it's always moving our oil down back where we want it. So easy thing to check for, and it's an easy fix if your customer says, hey, we have an oil leak, we can't find anything else. You're not going to hurt anything by machining a slight taper here, and you may well fix it. Ugly truth here. Last person to work on this motor might have flipped the bearing carrier over, installed the thrust bearings on the bearing carrier, mounted the bearing carrier, and then realized he's got a part left over, this splash plate. If we have drilled and tapped holes around the bearing housing portion, someone's left something off, probably a splash plate. So that splash plate, higher RPM, higher peripheral speed, multiple thrust bearings, we're more likely to see that splash plate. So that's something to really look at. The other thing I think worth just mentioning, and it's not bearing related, but worth mentioning, is if you look at the air baffle, when you're preparing to assemble this motor, put a dab of silicone at the bolt holes before you put the baffle on, bolt it. That way, if the bolts vibrate loose, screws fall out, then your silicone's still going to hold it in place. And it also eliminates that annoying air baffle rattling noise that you might sometimes hear. So not bearing related, but worth mentioning. Shaft currents. This looks for all the world like a bearing failed and the shaft drug on the end bracket, but what we actually have here is a sufficient energy circulating current voltage through the bearing housing, shaft, and if we insulate one end and we have it on a VFD, or if we insulate both ends and don't add a shaft grounding brush, then that voltage is still going to build. Think of it like a capacitor, and it will discharge across the closest gap, which is liable to be where the shaft passes through the end bracket. So here we have what amounts to electrical discharge machining with that repetitive voltage discharge across the surface from the bearing bracket to the shaft. So if we know we've got a motor on a VFD, if we diagnose shaft currents including in the bearing, we want to insulate one bearing, add a shaft grounding brush. We can use the hybrid bearing, which is probably the best option if it's on a VFD, and if it's not on a VFD, then the coated bearing is fine, or we can do some combination of the above. Low tech. Customer calls, hey, we just bought this new motor, we installed it, we're picking up evidence of shaft currents. Have them drop the drive carrier frequency to below 2 to 5 kilohertz. Most of that stuff's going to go away. So it's a quick temporary fix. We may want a dedicated high frequency ground strap. So basically going to look like a braided battery cable to properly ground it. And we really want to run a ground all the way from the frame of the motor to the case of the drive. Different types of shaft grounding brushes. I'm really not going to drill that deep into those. Another mechanical issue here is unique to verticals, and that is that resonance. We have a vertical motor maybe sitting on a tall pipe column, and if it happens to be running at a speed that vibrates its natural frequency, you get a lot of vibration on the top end and less if we take readings coming down towards it. You can use modal analysis, and you may well find that when you look at the vibration, it's going one direction, and maybe it's in line with the access hole in the pump housing. So there are a lot of things to look at here. That would be a Gene Vogel webinar to talk about. One thing that's low tech but very effective is to add a 2 to 8 inch thick steel plate under the motor base. It's going to lower the center of gravity, changes the mass, and changes the resonant frequency. So it's a low-tech technique that manufacturers have recommended really for decades.
Chuck, got a question for you. Do you need 2
Yes.
insulated bearings and shaft ground, or just 1 insulated bearing and shaft ground?
Okay, really good question. So if it's not on a variable frequency drive and what we're dealing with is truly a circulating current, all we have to do is break the circuit, stop the flow of current, like turning off a light switch. Real straightforward. If it's on a VFD, then the recommendation is to insulate both bearings and add a shaft grounding brush. And the reason we insulate both bearings is it's that capacitance that we're dealing with. So this voltage builds up, we're charging a capacitor, i.e. the winding is one plate of a capacitor and the frame via the slots as the other, and the insulation determines the capacitance. So if we insulate one end, we're breaking the circuit, but we're still charging that capacitor. So we really want to insulate both ends. With a vertical, that's tough. We can put a hybrid bearing in the bottom, but in the top, if we insulate the housing, we always have to be aware of the compressive strength of the insulation that's supporting those thrust bearings. The manufacturers who build the majority of vertical motors, both of them use a ceramic or aluminum oxide coating on the bearing carrier as a way to break that circuit, to insulate it. And that's something you can have if you have a specialty outfit around you who does plasma spray, they can do a ceramic or similar non-conductive material spray to the bearing carrier. So really a good question.
I got another one for you. It's can submersible motors used with VFDs be equipped with shaft grounding devices?
Submersible motors, yes, with a caveat. There can be a problem if it's an oil filled, because you have to keep that shaft grounding brush, whichever type you use, you have to keep that fairly free of contamination. And of course, if it's inside submersible, then that's going to be difficult to do. You can, you probably should deal with the different bearing shaft grounding device companies to see which one might encourage that. The only I've modified in the past where what we did was used a shaft grounding type of brush, the highly conductive material, in the cap where the brush was making contact with the end of the shaft. So it was above the upper bearing and it kept it out of the whole lubricant area, but not something we see as often. So assembly, we want to set the in play, the in thrust. Usually we're in that 5 to 10 thousandths range, but don't get hung up on 5 versus 6 or 10 versus 12 thousandths. Make sure that we put the angular contact bearings in the right orientation. And remember, the way they came in is not necessarily right. So if the customers had problems, we want to go back to the OEM or call ESA Tech Support and we'll help you. Changes in the oil viscosity. If we use a thicker oil, it's going to raise the temperature oftentimes. If you have a motor that is 20 or 30 or more years old, don't necessarily trust the manual. I know of one manufacturer with a large vertical motor where they changed the oil recommendation from an ISO 90 to an ISO 120. And that was within the past about 15 years, maybe within the past decade. Don't let anybody mess with the metering holes. Don't drill it out. And you don't want some mechanic to say, oh my goodness, I'm going to drill a bigger hole to get more oil in, because they're going to create problems here. If the bearing's insulated, check the integrity of the insulation, use a Megger. If you've got a megohm or higher, then you should be fine. If you have cooling tubes, make sure that we're always testing those for leaks. Thrust bearings, springs, that sort of stuff, the anti-rotation device, and then make sure that everything rotates pretty freely. We want to bump it for rotation before we put on the anti-rotation device. Watch out for the release type coupling. So you may have a coupling top half that just sits on top over some pins, and without the pump shaft and everything installed with it, you certainly don't want to risk trying to run it. Some manufacturers do use a steady bushing, so it's important to talk about that with your customers. Some people really don't like them, other people do. So I think that's important here. And again, the pilot bearing, just as review, the whole purpose of setting that in thrust is to lift the shaft and have room under this for thermal expansion. And again, if we have one thrust up, one thrust down, one thrust up, 2 or 3 thrusts down, then the outer races have to be clamped. The inner races should be secured on the bearing carrier. And we generally are going to see what you see in this image, where the bearing carrier shoulders against the shaft. So that takes away that 6 to 10 thousandths adjustments. We want to watch that. And the only reason I added this slide at the end is just to reinforce telling the customer that it may take an hour or longer for the oil to seep through and fill the inner portion of this chamber. So they don't want to get in a hurry. They don't want to just fill it to the fill level and call it good and fire it up, because they may still be a gallon or 2 away from the proper oil fill. All right, well, thank you for attending. Do we have more questions?
Yeah, we got a couple here. The first one is, why not choke the currents from the VFD, the source of the currents, a solution for submersibles too, for example, Cool Blue?
I think it's a good point. Not to endorse a product, but we've had ESA member shops who have done quite a bit of engineering study and found that those inductors, those chokes, work pretty well. So, and again, there are different options, and certainly that's one that seems to be viable. And with the whole long cable run issue, then that I think is certainly something to look at. Yes.
Next one, on a large vertical high thrust motor, what would be the purpose of an angular contact spherical roller bearing in tandem with a deep groove ball bearing on the non-drive end And what would be the purpose of having a 30 thousandths of an inch looseness on the housing for the angular contact bearing?
Yeah, that's a really good one. Whoever asked this, if you want to contact me offline, I can share with you a set of instructions shared by a warranty administrator for that manufacturer in which they recommend doing away with that ball bearing. What happens is the ball bearing is there to guide everything and keep it centered, and that in conjunction with the oversized housing for the spherical, in theory, the spherical then is just carrying the thrust load and the ball bearing beneath it is keeping everything centered. But what's happened in practice is with the amount of weight suspended on these bearings, it sort of self-centers that spherical thrust bearing on top. And most manufacturers just use that spherical thrust bearing on top, even in conjunction with a 20 or 30 thousandths oversized housing, and allow the geometry of everything to keep that upper thrust bearing centered. And what they found in practice, that particular manufacturer, was that the ball bearing kind of prevented that spherical from being able to center, and we wound up with with an elliptical loading issue on the spherical and short bearing life for both bearings. So yeah, not to be long-winded, but if you'll email me after we finish up here, I can share that that warranty administrator's information with you. They also
Uh,
changed the viscosity of the oil in that particular motor. So go ahead.
well, we just got
Next.
time for one more. The question is, if you have a down thrust bearing with an up thrust bearing, which one goes on top and which one goes on bottom?
Okay. Even though some of ESA's graphics are contradictory, if we have one thrust up and one thrust down, we really want the thrust up bearing on bottom because most of the time it's not doing any work, so there's little friction. So if we put that on bottom and the thrust down bearing on top, now we're getting cooler oil to that upper bearing. Whereas if we flip them, then the loaded bearing on bottom is transferring heat to the oil, which is in turn transferring heat to the upper bearing. So one up, one down, you want the thrust down bearings on top.
That's about all the time we have for this session. There were some other questions, and I'll give those to Chuck. Chuck will be at the
Okay.
Open Tech Forum. That's going to be on Wednesday morning, so he can maybe address those extra questions that came in then. And we invite you guys to join us in about 13 minutes for our next session, which is going to be in Spanish. And it's going to be on stator core testing, know what you have before you wind it. And that's going to be presented by Carlos Ramirez at noon Central Time. Thanks again, Chuck, and thanks for everyone attending.
Thanks, everybody. Take care.